Hey there! Ever stop and think about how all the gadgets in our lives actually work? You know, how your microwave knows you hit the popcorn button? It all comes down to how these things can sense and react to the world. Today, we're going to dive into microcontrollers, the tiny little brains inside almost everything, and figure out how they listen to us and how they talk back.
So let's start with the most basic thing you can think of. You push a button. How in the world does a hunk of silicon and metal actually feel that? It seems so simple, but it's the perfect puzzle to get us started on this whole journey of machine communication.
All right, our first building block is the good old-fashioned switch. You'd think it's just on or off, right? Simple. But, well, getting that simple on-off signal into a super fast digital brain without confusing it, that's where things get interesting.
Take a look at this circuit. This is where the magic really begins. You've got your switch, obviously, but the real hero of this story, the component that makes it all work reliably, is that little guy right there, the pull-up resistor. Think of it as the gatekeeper for the microcontroller's input.
So, what's this gatekeeper actually doing? Well, without it, the input pin would be floating. It wouldn't be high or low, just kind of there. It'd be like an antenna picking up all sorts of electrical noise, giving the microcontroller garbage readings. The pull-up resistor fixes that. It firmly connects the pin to a high voltage, say plus 5 volts, giving it a clear default state. Let's break this down. On the left, when the switch is open, when you're not pressing it, the pull-up resistor keeps the voltage high, so the microcontroller reads a digital 1. Clear and simple. Now check out the right column. When you press that button, the switch closes, and it connects the input pin straight to ground or 0 volts. That makes the input low, and the microcontroller reads a 0. And that resistor, it's now doing another crucial job, preventing a direct short circuit between our voltage and ground. So cool! It's a really elegant way to get a clean 1 or 0.
So we have our clean signal. We're done, right? Well, not so fast. There's a hidden problem, a little gremlin in the system that comes from the fact that we're dealing with a physical, mechanical thing. Let's talk about something called bounce. And here it is. The digital brain, our microcontroller, is incredibly precise and mind-bogglingly fast. But the real world, the physical world where two pieces of metal have to slam into each other, that world is messy. It's not clean at all. You see, when you press a button, those little metal contacts inside don't just close once. Think about dropping a basketball. It doesn't just hit the floor and stop, right? It bounces a few times. Switches do the exact same thing, just on a tiny, super fast scale. They make contact, bounce off, make contact again for a few milliseconds before they finally settle down. And this is what that mess looks like to the microcontroller. To us, it's just one single button press. But to a chip that's checking that input millions of times a second, it sees a frantic storm of ons and offs. This can be a huge problem. Imagine you're building a scoreboard and one press of a button adds 10 points instead of 1. No good. Fortunately, we've got a couple of great ways to fix this. On the software side, it's pretty simple. You just tell the code, hey, once you see a press, just chill for a few milliseconds. Ignore everything until the bouncing stops. The other way is with hardware. You can add a small capacitor to the circuit, which acts like a tiny shock absorber, physically smoothing out those voltage spikes. It's that classic engineering trade-off, a simple code fix or a more efficient hardware solution. Okay, so we've totally mastered a single button. But what happens when you need more, like on a TV remote or a calculator? You don't want to use up a dozen input pins for a dozen buttons. There has to be a smarter way, right? And there is. It's a really clever setup called a keypad matrix. Instead of giving every single button its own personal wire, we arrange them in a grid of rows and columns. This is a game changer for efficiency. Check this out. A 12-button keypad, which you'd think needs 12 pins, can actually be read with just 7. 4 for the rows and 3 for the columns. That saves a ton of I/O. And here's what that matrix looks like in a diagram. You can see the grid pattern with the rows and columns each connecting back to the microcontroller. Every button sits at an intersection of a row and a column. So how does the microcontroller figure out which button you pressed? It's kind of like a teacher taking attendance in a classroom. The microcontroller calls out one row at a time by making it low. Then it quickly checks all the columns to see if anyone raises their hand by also going low. If it finds one, boom, it knows the exact key that was pressed based on the row and column. If not, it just moves on to the next row and does it again, all in the blink of an eye. Awesome. Our machine can now listen to us whether it's one button or a whole keypad. But, communication is a two-way street. It's time to figure out how our project can talk back to us. Let's look at displays. This here shows the evolution of a machine's voice perfectly. On the left, you have the iconic 7-segment display. Think digital clocks, ovens, great for showing numbers. But on the right, you've got an alphanumeric LCD. This is a huge leap forward, letting our devices show us full text, symbols, you name it.
And they each have their own strengths. The 7-segment display is super simple and tough as nails, perfect when you just need to show some digits. The LCD, on the other hand, is way more powerful, but it's also more complex. It's got its own little controller chip inside that you have to talk to, and it even has clever tricks like a 4-bit mode to, you guessed it, save on I/O pins. So, when you boil it all down, from the simple click of a switch to a complex message on a screen, this is what it's all about. Inputs and outputs. They are, quite literally, the senses and the voice of any electronic device. Understanding this is the key to building, well, anything. So there you have it. We've seen how a machine can feel a button, how it can read a whole keypad, and how it can talk back with the display. These are the fundamental building blocks of interaction. The only real question left is, what are you going to build with them?